Okay. خلاص محمود, okay? Okay. We start more or less from where we stopped yesterday. We said that we had a universe that was homogeneous and isotropic and was self-similarly expanding, meaning all scales expanding at the same rate, at the same speeds. And there were two parameters really: the density, because it's homogeneous, there's no scales. The scales in radius are not important, or in time other than through the density. And there was a constant that was defined for all scales, for all spheres, for all expanding spheres. They had a constant that was characteristic not of the scale of the spheres, but of the scale of the universe, the radius of curvature of the universe. It turned out to be, when I did a little schematic GR, that it's related to the inverse of the time square that the light takes to cross the radius of curvature in a closed universe, or the character scale in an open universe. It's of course infinite in a flat open universe. Okay, so therefore the curvature must be related to what else? To the density, because you only have these two characteristic parameters in the problem: curvature and density. And so we said we could perhaps try to find an observation. What's this density that is critical, that makes the curvature zero? Spatial curvature zero, a flat universe. And what beyond it, a density that is larger than this critical density, you had a closed universe, like a hypersphere, a three-sphere, or if it was less than critical, you had an open hyperbolic universe, like a saddle. Critical density is what makes the curvature K zero. In our convention, that was 1 over r squared, or the radius of curvature being r, related to the scalar curvature, the two-dimensional curvature, which is also called the Ricci curvature. Okay? Scalar curvature. And by putting rho c here and putting this to zero, just by definition, this is our critical density that makes the universe flat. And you can define the other densities in terms of it, and you said if we start flat, we remain flat. If we start curved, we remain curved, because of this equation here. And you cannot turn from one to the other, but if you inflate a lot, a curved space can appear flat because you inflated it beyond measure, so to speak, that it appears flat, not curved anymore. Okay? But otherwise, a curved space remains curved. And we said that a long time ago, about when I was your age, about 30 years ago or so, people tried to get from redshifts, which we'll speak about today in more detail, the Hubble constant, which enters into this thing. So they tried to find this equation, the Hubble constant, to see, and the density in the universe, to see if omega was greater than 1, ball universe, less than 1, saddle universe, 1, flat Euclidean space. Not space-time. Space-time is always curved because of the dynamics. Okay? Okay. So we said this didn't work at all because, first of all, we didn't know that some of this rho is in forms that are not, we cannot find them by doing a budget. This galaxy is this mass, maybe there's a little bit of dark matter, so multiply by 10, do the dynamics maybe on large scales and see how things are moving, so we do a dynamical mass. That's what people are doing. Add it up, and here's my rho. Well, it turned out to be much less than 1, and inflation people were really angry because they wanted a flat inflation one. Alexei will speak about inflation later. They wanted a flat universe. Well, it wasn't flat, it appeared. And the inflation people are angry, but the observers said that this is how it is. Some others said maybe there is some extra material that we can't count. We can't see it like that. So how do we see it? That's the question of today. One way of seeing it is today's lecture. The extra material that cannot. It turned out to be material in the end. I'll give you the answer of this sort. Not necessarily a cosmological constant, but something similar to it. That is quite exotic form, that the density doesn't decrease as 1 over the volume like in normal matter or radiation, for example, 1 over volume, then the redshift, so 1 over volume times the distance, so 1 over 8 to the 4, but a constant, which is a bit strange. That's how it is. And they got a Nobel Prize for this in like 2012, I think, the people who did it. So the idea is you want to solve this equation and compare it to observations, basically, to fix our parameters. You want to fix our parameters. What is rho made of, really? How much normal matter, how much of this exotic cosmological constant. In principle, how much radiation, but you don't do it by the methods of today, how much radiation. There are other methods. But whatever else, and this is ongoing. Like, for example, Euclid, which was launched 2 weeks ago, or 3 weeks ago, will try to find if this is really constant or not. So this is a project that is ongoing, and Euclid, just to give you an idea of how this Euclid is dramatic, in 2 days it will make observations with the same accuracy, with the same resolution that the Hubble Space Telescope did in 33 years, in a third of a century. And it will go on for 6 years for mission time, okay? So this Euclid is not trivial. It's at least as important or as important as the James Webb and so on. And it will get the same sort of publicity once the images come in. The images are not coming in yet, because it's just 2 weeks ago. Okay? So the main thing of Euclid, Euclid will not mainly be discussing, it's not launch purpose for the things discussing today, but the things of next week more, like the structure formation, the perturbed universe. But what the main thing, other than testing models of gravity, which is another thing that could be instead of cosmological constant, it can change the gravity. It will look if this is really a constant or nearly constant or not, a scalar field, for example. So we don't need this 10 to the 100th problem that Alexei was talking about. Maybe it's just 0, and what's doing like a cosmological constant is some other scalar field that we don't know, or modified gravity or whatever. So this is going to be tested in the next 6 years quite rigorously. Okay? But let's start again with the simple stuff we said last time. We put an equation of state, because you need an equation of state to solve our equation. We need to see how our components vary. In the standard cosmological model called lambda, CDM, lambda is the cosmological constant, CDM is the cold dark matter that we'll speak about next time. It's thought to explain these rotation curves of galaxies and so on. So the CDM is this, the matter, mainly, and 5% baryon. We'll talk about that much more maybe later today and also next week. So this is the matter. Then there's radiation, which was really important in the early universe, but it's not important anymore because it goes as 1 over 8 over 4. And there's this vacuum, the cosmological constant, which is small, but being constant starts winning out like a few billion years ago, some 5 billion years ago or something like that, of this order. Okay? So this is the current picture. And this, let's take a flat universe. And so the equation is easy to solve. And put the different radiation, you get this sort of behavior. You just try power law solutions and you get that. And find the index. Just say A is equal to that. You say A equals rho is proportional, let's say, to A to the minus 4. So you put it here and you integrate just and you get these things. Okay? So you get T to the half for radiation, T to the 2/3 for matter, and quite importantly, for the cosmological constant and for early inflation, they're similar, you get exponential inflation. So, basically, if you put rho as constant here, can you see this? You get a log equals something. So therefore, A is exponential in time. Can you see that? Or is it? I think this should be. You just put rho as constant here. This is an exponential solution. And H is A dot over A. So you put H equals constant. Okay? So that's fine. For the three, so we have in the very early universe supposedly vacuum domination, and you have inflation and so on, and then you have radiation domination, and then you have matter domination, and then you have recent cosmological constant, which is why, at least in the standard models, the cosmological constant, which is why people couldn't find the whole row, because it's not in matter, it's in something else. It could be vacuum energy, it could be a scalar field rolling down, it could be modified gravity, nobody knows. It's one of the biggest research subjects in the next few years, in the next decade. Right? And could lead to a very big, thing. Okay, so basically these are inflation solutions, exponentials. Okay, so to start to fix our model, we need to relate this A of t to observable. You can't really observe this A of t. It's a scale factor of the universe. How do we relate it to things we can see? Okay, so that's the subject of today's lecture. The object of that is to determine the content of the universe, this rho naught now, and rho before, hopefully, what it was made of, what it is made of, and the age. And the expansion rate, they're connected, the age and the expansion rate. So how do we do that? First of all, you need some definition. There's something called the conformal time, which is important in FRW cosmology. It's really a distance, but they call it time probably because it enters instead of dt here, and they call it conformal because the scale factor, instead of multiplying only the distance side of the metric, the space part, it also multiplies the time now, all of it. So this is a conformal metric because everything is multiplied by what's called a conformal factor. So this is called the conformal factor. You take this definition of the conformal time, you put it into that, and you get a conformal metric. That, if you remember, was the FRW metric that determines distances in FRW universe, which for a flat universe is really only Minkowski written in spherical coordinates. But for non-flat universe, it's a bit different. So, and this is our radius of curvature that we search for. Okay? So connected to the conformal time is a co-moving distance. Now, which is a difference of conformal time. Conformal time is the co-moving distance that the light traveled since the beginning of the expansion to today. If you write in the convention that A of t, the scale factor is 1 dimensions. Last time I told you about the conventions. I'm using this convention of A of t is 1 today. This means this is the light, this is the distance the light traveled from the beginning of expansion to today. Okay, in today's length scale. You need to define what length scale because the universe is expanding. So in today's length scale. بالفلاحي لو عندك جنيه في البنك في مصر حطيته من سنه 60 لغايه النهارده مش هيبقوا 60 جنيه عشان الانفليشن. بس خلي بالك دي مش انفليشن زي الانفليشن كوزمولوجي. بس هتبقى قريب اكسبوننشال ان شاء الله. It will be, but so this is basically the same in very heuristic terms. This is distance in today's measure. And it's a geodesic distance, so it's invariant. So look at co-moving distance between us at time t naught now and somebody or something that emitted light at time t is the difference in conformal times. Okay? And it's an invariant geodesic distance. But it's not measurable directly, we're not there yet. But it relates to things that are measurable. Okay? So that's important. And it's invariant for a given cosmos. By definition, it's in today's currency. So it's invariant. So this is the distance taking into account the expansion of the light traveled between times t1 and t2 or t0 and t0. Okay? So there is horizons connected to that. We saw the Hubble sphere before. The time of the expansion, the length of an expansion in an expansion time, and it was connected to the Newtonian approximation. We said that the distance between galaxies shouldn't be larger than that, otherwise the universe would be expanding faster than what light can communicate between things, meaning not expanding faster, changing its scale faster than the communication time between galaxies. And our particle horizons, so in the sort of normal universes, say, things like that, matter radiation, things that are not expanding faster than t, basically, actually, less than linear, and decelerating universes, where normal matter decelerates and the rock thrown up like the door, not something accelerating like inflation. This is finite. If you put 0 to any time tf equals now, 0 to now, for example, this is finite, meaning there's a finite distance you can see. There's a horizon. You can't see beyond that. It's a time, it's a distance, that the co-moving distance that light took to travel from the beginning, so to speak, or beginning of expansion to now. And you can't see anything before that. And not before that, I mean further than that. Now this is about, if you calculate it, it's about 14 gigaparsec co-moving. This is much more than 3-4 times, 3.5 times or something, more than the time in light years because of the expansion, okay? So this is in co-moving distances. So why is it not 13 giga light years? No, it's not. It's 3 times. But it's not much more. If we were inflating, it would be actually almost, not almost, it would be forming infinite in inflation. You could see very far back. But that's why, but you can't see much. It would be very far back, but redshifted infinitely, so you can't see anything really. So in a de Sitter universe, an inflating universe, you have a future horizon, so to speak. Things happening now you will never see because they are outside. The thing is inflating exponentially too fast, and زي فلوسك اللي هتروح كده. Okay, it will just go away. And things inside the horizon will inflate also away in a de Sitter universe, as you learn in inflation. Okay, and therefore things that were in the horizon very long time ago, but now escaped, you can still see them, but you'll see them really redshifted, really very far away. You can see infinitely far, but you see nothing. In fact, if you continue with lambda CDM, as I was telling somebody yesterday, if you continue with lambda CDM and lambda dominates for another, I don't know, trillion years, you won't see anything in the universe. Astronomers will only see the Andromeda galaxy maybe, and the galaxies nearby, which are gravitationally bound. Everything else will just go away, out to the horizon. Okay, so that's a little fun. Now back to the boring data stuff.
So what we can observe is getting less and less.
Yeah, it's getting less, but we'll die before it. We don't see it. It's another 1 trillion years, so you'll be fine. But yes, we are seeing less and less, and this is one of the ways that people are testing. cosmological hole. How far are we seeing less and so on? There's some precision. Okay. So, right. So, okay. So back to our fundamental equation, the Friedman equation, or some people call it second Friedman equation. I call the other one the acceleration. The Friedman equation. A squared equals A dot over. This is our energy equation بتاعت الطوبة خلي بالك. Just to see how powerful this tuba is. This is the energy equation. Okay? And this is the energy in Newtonian terms. In GR, it's now we define things in terms of our rho c, the critical density, the density that makes this zero. Put this zero and define this. Nothing really tricky in that. And you define it naught because today, T naught. Naught refers to today, current universe. And you can do this with the omega matter, you call it omega m naught, omega radiation, omega of the curvature, which is this term here, and omega lambda of the cosmological constant. How much? This tells you the relative contribution of each term today compared to the critical density. If you all add up to 1, then it's a flat universe. More than 1, it's a ball. Less than 1, it's a saddle. Okay, and then you can write your thing like that. Why do you write a thing like that? Because we know radiation goes down like that. Radiation goes down like that. Matter goes down like that. Curvature goes down like that. Lambda doesn't go down like that. So, okay, so we wrote, this is all we've done, we wrote this like this. Okay, then we can notice that dA by dt is AH and put it here and guess this equation and write it like this also. And I took the zero out here and write the co-moving distance. So we now have the co-moving distance. That tells you the distance is in today's terms. In terms of the contents of the universe, we're making progress. Okay? We're making progress. We're getting some distance. And you can get the time you do it. So you can get the age of the universe in terms of its content. It looks like that. It's very easy. Now, you have time there, A dot. Okay? So just integrate it. So this is the time and this is the distance in a Friedman universe. So you can see, at least in principle, if we know how much radiation there is, and matter, and what's the curvature, which is really, this is omega total minus 1 is really the curvature. Okay, so it's actually not dependent. This actually is dependent on that, not independent. And if you know how much cosmological constant there is, then you can know the distances to things, theoretically, and you can also predict the time, the age of the universe since the beginning of the expansion. Okay? And this just says that these are dependent from the total temperature. So you have really, and radiation is almost zero today because it's going down as 1 over 8 to the 4. So really you only have two things, and the DH here, the Hubble parameter, the Hubble sphere. So the Hubble sphere, our Newtonian limit sphere. And so you need to know the Hubble constant and omega lambda and omega matter, really. Only 3 parameters in the end. Okay? To determine your distances and age and so on. So you need to compare with data. So you need to first find the scale factor as a function of an observable. You can't see the scale factor. So what is observable that you can see a scale factor? And also relate to co-moving distance to things that we can see. Okay? How do we do that? First of all, the redshift. We saw this thing. This is a galaxy emitting some line element, spectroscopy, You did spectroscopy? Spectrum. It's a spectrum. طيب زي بتاع الأرض يعني بص طبعا. And the more it goes to the right, the further it is. The further the galaxy is, and the more fast it's moving from us or expanding. So this is the picture, schematically. And light gets stretched like that. Blue shifted, the thing is moving to you, red shifted, if it's far. Now, we said Andromeda won't inflate away in the Sitter universe. That's because it's gravitationally bound. So an important thing, this room is not expanding, the solar system is not expanding, the galaxy is not expanding, Andromeda and us are actually merging, not expanding. It's on large enough scales beyond the 10 megaparsecs, things are the sort of the order, which is 30 million light years, that things are expanding. So these galaxies have to be far away. Things are not expanding here, okay? Okay, so how do we do it? There's a heuristic, very simple way of doing it. Lambda 1 is just things are emitted at T1 have an A1 scale factor, and things received at T0 have A0 scale factor. So the redshift is simply A0, A of T0 over A of T1 times lambda 1. And this is really the redshift. And we define it like that. The differences between frequencies. The frequency we receive and the frequency we know these lines. We know this is sodium, this is whatever. So we know, okay, from laboratory spectroscopy. And so, simply 1 plus z is this. Okay, so we can get, in terms of the frequencies we see, we can get the scale factors. We're making progress. Our scale factors are now being determined in terms of observables. And you can do z dot here and expand z, and you find by multiplying c that the time light takes to come from the galaxy in the linear regime, we're expanding for small t emitted minus, or t now minus t emitted, we're expanding for small f, should be a linear thing which Hubble discovered. That's why it's called the Hubble constant. Times the distance is approximately equal in this for nearby galaxies, relatively nearby, times the redshift speed. Okay? So from that you can get the Hubble constant. You plot the distance compared to velocity, which is a redshift that you see, CZ. So you plot this against this, and this is like you do in the lab, you know. علاقة خطية وده السلوب بتاعها. This is the slope. So this is the Hubble constant, okay? In elementary terms. Right. So this is historic. More formal thing of doing this, you can do it through the conformal time. So this the distance between us and the thing is invariant. This is the conformal. This is the co-moving distance. So you take the differential here, which has to be 0, and for assuming that that they don't move much, the galaxies during the time the light is emitted, which is in nanoseconds. So you get a relation between the time scale, the redshifting of time scale from the rest frame of the emission to our frame, which is the receiving. And this is a frequency, which is an inverse of a wavelength, which is therefore relates again your. So you can get it heuristically or get it more formally from the differences and how time is measured in the local frame there and in our frame back here. Okay, whatever you prefer. After you've done that, we need distances. Now we know how to relate A to Z. Okay? And Z can be measured. Z measured, Z relates to A, we're done. And we usually take A not to be 1, so we're done really. For any object we measure in the redshift, we can know its scale factor. Okay? Up to the definition of A naught, which is not a big deal. Because we will be able to use scale ratios. Now, two main distance measures are done in cosmology, or astronomy in general, actually. There are others, but these are the most important. There's something called angular distance, and angular diameter distance, and luminosity distance. And they're very simple, actually. If you see an object at a distance delta theta, and it looks like its size is A, or you know its size of A, then the angular diameter distance is this. So small angle that. Really? Okay. Right? Easy. زي المقاولين. Okay? This is a luminosity distance, also very simple. The light on a sphere, the intensity or the flux per unit area of the light on a sphere is conserved so that it goes down like Newton's law over distance squared, because the sphere grows as the distance squared, or r squared, so it diffuses. Okay. So very simple. So lambda meet watt at 1 meter will look like 1 watt at 10 meters. And this is just regular Euclidean distances and so on, and nothing really tricky about it. It's a bit slightly tricky if we do cosmology, so you have to take care a bit, because you need to, if the universe is not flat, then the geodesic distance is not the same as the Euclidean distance. Okay? So you, but you use the Euclidean distance, which is, so again you use the same definition, which is what you measure, because the angle is actually still defined in Euclidean distance, but it's not the co-moving geodesic distance anymore. That's the main difference. And you do when the light is emitted at A equals C for the angular diameter distance. So it's the same lasers thing, but you measure when the light is emitted, okay? Because you want to measure its angular size. Okay, so the definition becomes dA when is the thing of the arc length here, the radius of the arc length, the r going into the theta here. Okay. So r d theta is our measurement. Like it becomes that. And there is the redshift. So you have 1 over 1 plus z, or a. This is r a equals 1 plus z. A equals r, or 1 plus z. Same, not same, but similar to for the cosmological luminosity distance. Now, the angular diameter distance we won't use really today in cosmological sense, but we use it next week for the cosmic microwave background. Today we will be using this luminosity. So take our metric again, and we want to have the same definition. This time, the light is spreading on its journey from emission to reception. So we want to take A equals 1. In our definition, A equals 1 is today. So you want to take what you receive, the light, how much energy you get. Okay? And again, use the area element here. The area element, the thing multiplying d omega squared, which is r squared. Where is r squared? So it will be r squared, but there are two other effects. Here, in angular diameter distance, we don't take into account these effects because it's not important the energy, the photon, the number of photons coming in. We are looking at sizes. But here we're looking at energy. So it's important to notice that the energy of the photons is redshifted on the way from being emitted from the distance luminosity thing, the standard candle light far away. On its way here, it's not only spread, but it's also redshifted. So its energy goes down by a factor of 1 over z. Okay? And then also the number of photons arriving because of the expansion is less. The rate arriving is less because you're moving away from it. So it's another 1 over z. So 1 over z squared, so dl becomes r, the radial coordinate, or therefore w, times 1 plus z. So it's 1 plus z squared times dA, the angular diameter distance. This thing. All right? Okay. So what we've done now, we got A as a function of the observable z, the redshift, redshifting of light. Oh. And we got the luminosity distance, something we can observe. Observe it. Yeah? If we know something, how luminous it is intrinsically, and then a standard candle, standard lambda, we know it's 100 watt, then you can know it's 10 meters away, right? So we know that we can observe this. If we have a standard candle, I'll talk about the standard candles, but let's say we assume we have the meat watt, 100 watt candle, okay? And now we're related to the theory R, which is distance determining the area element, and Z, which is another observer. So what is R then? We want to relate R to the co-moving distance. R is that. Flat universe is just a linear relation, sine and sine for the ball and for the sphere and saddle. Okay? And and this in turn is related to our co-moving distance that we can calculate theoretically. Okay? To the matter in the universe and the cosmological constant and the Hubble constant and so it's nice. We are getting a relation between standard candles and dark energy, you know? And R, which is this radius of curvature thing. Okay? But R is easy actually because simply you get it from the Hubble sphere. So from the Hubble constant. It's one of the Hubble sphere is CH2. R is connected. Then you need the co-moving distance, but we know it. Now we write it in terms of Z directly. We leave A alone now. We don't talk about A anymore. We put Z. Because, as we said, where did we go? This. Right? So Z is 1 plus Z is A. 1 over all plus Z. 1 over. So we put it in our co-moving distance equation. So we have Z, and this is the Hubble constant. So by assuming or knowing, whatever you like, but assuming is better for our purposes, a matter density and a cosmological constant density and a Hubble constant, we completely define theoretically our luminosity distance, which for a given redshift, which we can compare with observed luminosity distance and try to fit it to get what is really omega m, omega lambda, and h naught in our universe. Okay? So that's a good song. We have been able to connect A to Z and DC to DL. And once we've done that, we can start. But we need a brief interlude now into astronomy to see what are these standard candles and what do we do. Now this has been a project that's been going since the ancient library of Alexander. How do you determine distances to the moon, to the sun, to the stars? Again, Aristarchus, Ptolemus, Euclid, people like that. So it's a long legacy of civilization. Astronomy is, as you'll see, we use the same notation in astronomy today that Ptolemy invented, more or less. The magnitude system that drives physicists crazy. So we start by this parallax was done by ancient astronomers in Alexandria. It's the method of the Nauli. It's similar to the angular diameter distance, but it is the angular diameter distance applied to nearby objects. So the Earth moves around the Sun, and because the Earth is around the Sun, a distant star will appear to be moving. From December to June, it will move a very small angle. And that small angle is, of course, related to its distance. Okay, so that's how you get the distance to near stars. But Gaia, which was launched like 5 years ago, is getting the distance to 1 billion stars like that. The whole galaxy taking, it's a galaxy has like 100 billion stars. It's taking out of these 100 billion, 1 billion, which is sample, respectable sample, and measuring the parallaxes like that, because it's very precise there. If you do it from Earth, you can only get maybe, I don't know, maybe how much? 100 light years, maybe? Something like that. Very small.
Much less.
I don't know. I don't remember. But it's small. But this gets you 100 kiloparsecs. The whole halo of the galaxy. 200 kiloparsecs. Which is much more than 100 light years. I don't know from Earth how much you can do. Not a lot. And you can do, what Hubble did actually was another very cunning, hidden thing, Cepheids. Cepheids are stars that vary in luminosity with time. You find their luminosity is periodic. They have like oscillations. They heat up and cool and heat up again and cool and so on, so they have a period of time. This period correlates with amplitude. I don't remember which way. Oh, it's like that. Okay, so it relates with amplitude. Okay, with of the luminosity. The average luminosity correlates with the period. So let's say you have a few Cepheids nearby that you can measure through parallax, the distance to. So this is called the distance ladder that we're doing. You have a Cepheids nearby that you can measure with parallax. And you make this plot. I'll tell you what this is later. This is like, for our purposes, it's luminosity. Okay? But as you can see, it's going the wrong way. For reasons that I'll tell you about. For reasons of the Alexander. Okay, so this is luminosity, and this is the period. So you can make this plot. Then, if you see things far away and you see the period, you can know the luminosity. But you know it's 100 watt, or whatever, 200. Let's say this is 100 watt, 200 watt, and this is the period, the oscillation length. So I measure the oscillation length, and I know how many watts I have. So I increase my distance scale when I see Cepheids far away. And that's what Hubble did 100 years ago, or so. Now, here's this thing from Alexander. Ptolemy classified the stars with apparent brightness. So he classified this. The highest is the brightest, number 1, 2, 3. That's why it goes the wrong way. Sorry?
What's the difference between the subs and similar?
Between what?
Subs and similar.
Stars and similar.
Subs.
No, they're very different. All stars are dead. They also they have only similarity in the time and the periodicity. But pulsars are dead stars that are neutron stars and very compact, and the emission mechanism is through a magnetosphere, very and relativistic and so on. No, these are simple oscillating. All those are actually rotating, and it's actually relativistic beaming. That's the reason they pop. It's relativistic. This is not a small star oscillating up and down in the radius of rotation. So, but it's not a bad question because both do timing. Yes, both have a timing. That's a common between. But there's no common physics almost. Okay. So this is the first. That's why it goes the wrong way, because he ordered them min ma'am to akbar. You know, يعني كانوا هيبة كده. He ordered 1, 2, 3, 4, not the reverse. Totally. And it defines a log scale because the eye sees on a log scale 1, 10, 100,000, million, and so on, not 1, 2, 3. So the eye sees on a log scale. That's why we use a log scale also. And in modern times, it's defined like that. The magnitude of the object minus the magnitude, absolute magnitude of the sun, is the ratio of the luminosity, assuming that the object is 10 parsec away. Because if it's a point object at 0, the luminosity diverges, formally speaking. This is a sphere of radius 0, so you can't. So 10 parsec, and therefore you can have, this is called the distance modulus, and this is relates to the luminosity to the magnitudes. Okay, so a really nice, of all people who did a nice historical review of this stuff is Steven Weinberg. because he's a curious guy, even though he's a particle physicist. In his book, Cosmology, the more recent one I did before he passed away, he has actually a nice historical review of this stuff and the different definitions and who did what and so on. Weinberg was a curious person. Okay? So here is some things you can do with this stuff. There's something called the Tully-Fisher relation, which, if you remember, we did in the first lecture. It's roughly speaking, comes from the Hero theorem, and it relates the absolute magnitude to the log of rotation velocity. And so if you see a galaxy rotating with a certain speed, you can know its velocity, just like the period of the Sheffield, but the whole galaxy. So you calibrate this relation locally, and you look at the rotation speed of a galaxy far away, and you calibrate it with the local relation. So this is another way you do a distance thing. So same limit. Okay. So and then the most important for our purposes by far is the supernova 1A. These are extremely bright. One supernova as bright as a galaxy. And when they explode. They explode the theory is that there are binary stars, and one of them is near the Chandrasekhar limit of degenerate pressure and so on, and where it should make a neutron star, but it doesn't. Or a black hole, it doesn't. It accretes mass, and once it gets to the critical limit, it cannot get rid of the energy. The Sheffields are normal stars; they can expand and cool, and then they will collapse. But it is supported by thermal pressure. P equals RT over mu. Temperature is regulated. There's an equation of state. A degenerate equation of state doesn't depend on temperature. So the whole energy.
So the Sheffield is like in check equilibrium.
It's a stable oscillation. It's a stable oscillation. Yes. This cannot do that because the equation of state is independent of temperature, of the electron pressure. It's through Pauli exclusion principle. So you can calibrate them. The nice thing about them is that their absolute luminosity correlates with how fast the light curves goes down. I don't remember the theoretical. Actually, there's a theoretical argument about exactly why among people who work on this stuff. But anyway, whatever the reason exactly why, because it's complicated simulations to get theoretically these light curves. And it was debated when they got the data from the distant supernova. It was debated by more than 10 years whether this was real or not. Because dark energy, this is not the joke. So, especially the physicists will say, "Are you sure? Are you sure? We thought it's 10 to the 100. Are you sure it's like that?" So, but the astronomers were quite confident. I remember discussions on it. But it took time. It took like 10 years of work before. And there's people even arguing today. but they got the Nobel Prize. They don't care. So. That's what I was saying. But the calibration is. Yeah. Yeah, and the physics is understood enough for there not to be something completely, that's to my knowledge. We can take a look at the recent literature. To my knowledge, it's reasonably understood. But there's a lot of work. And the simulations are complex and all sorts of stuff. Treating how the neutrinos be shockwave. It's very complicated. But in the end, here's the calibration, as you see.
The calibration curves are
Yeah, so, yes. So, knowing the stretching factor, you can calibrate it so that you know how many watts it has. What's absolute luminosity or absolute power, say, if it's in watts, of our standard candle or standard light bulb. If we know the stretching factor to make it fit here, this is another self-similarity solution, by the way, but of a very different type. These form a self-similar group of curves with two parameters, the amplitude and the stretching factor. So if you know one, you can get the other. Just like as we could know the density, we know the curvature, but in a very different context. But conceptually speaking, it's the same. Okay, so it looks like that. Redshift against the velocity distance of supernovas up to redshift 1 somehow, but this is like 3 or something like that. There's another slide where it will be there. Redshift 3, that's a long way, by the way. This is like 80% of the age of the universe. This is like, redshift 3 is like about 10 billion years ago, out of 13, 14. It's a long way. So this is how it looks like. These are the different observations from SDSS, from the Hubble Space Telescope. There'll be more, of course, from Euclid. Euclid will do some, but it's not its main goal, but it will do some. And there'll be James Webb, I'm sure, and so on. This is before that. Okay. I don't think there is yet any James Webb. I certainly know Euclid, but I guess there will be. Okay, so let's try to get a feel of what we're trying to do. We want to connect this to theory, as we said. The theory is the co-moving distance, which we write in terms of redshift, and we want to determine omega m and omega lambda and h naught. This is 1 over h naught, basically. So we want to determine, we have 3 parameters. To get a feel of how things go, I mean, we have to solve this numerically, of course, and then fit it with the ways of the maybe Mahmoud will talk about and even more sophisticated stuff, Monte-Carlo MC, and maybe in the future the sophisticated stuff that Hamad talks about and so on. But we are not there. We are just doing very pedestrian stuff. So let's expand it in linear series, and we get up to order z squared of this. So you can see if omega m is very large, this is 0, and this thing very large, say omega n is 4 over 3, meaning we have a closed matter-dominated universe. And say, so the whole thing, omega naught equals omega m plus omega lambda, is dominated. There's no omega lambda, and we only have omega m, which is 4 over 3. So this is 0. So this is all 0, and we just have a linear relation. If omega m is smaller because we added omega lambda, remember the total, there's a total. So omega m is small, and we added omega lambda. Then this will start being z squared, and will start being above it. That's in the linear regime. We go up to z equals 3, so it's not linear, but just to get an idea of what we expect. Okay? So we expect that what used to be called the standard CDM, omega lambda 0, omega total 1, a marginal flat universe made with matter, maybe called like matter, but doesn't matter. Called like matter plus everything else, the standard model and so on. That's what used to be called the standard CDM, like up to year 2000, say. Huh? But in the last 23 years, in your time, it's not called standard anymore. This is called standard. Why? Because this one doesn't fit. This is almost linear, like we said. Right? This one doesn't fit. This one fits. Omega lambda, 70%. Omega matter, 0.3. And a Hubble constant of 73 kilometer per second, or 74 kilometer per second per megaparsec. Which we may talk about different ways of getting it, and big arguments about disagreements and so on, but that's not our subject today. Okay? So, because you can see, these are called residuals in statistical measure. So this is the best fitting model minus the data. As you can see, this standard CDM is really a poor loser. Very far from the data. There's more than 2-3 sigma for many, many points. That makes it really unlikely. It's not 1 sigma for 1 point. It's 2 sigma or 3 sigma for many points. There are things that are a bit reasonable. In fact, The omega lambda alone is not very bad, but you have to have a very small number. An empty universe is not too bad, yeah. So it's very delicate work. Okay? But the lambda CDM is perfect. It's a perfect thing. No residual. Almost exact. So that's why we think there is a lambda, and that's why they got a Nobel Prize for it. And the lambda is determined at 70%. So the parameters is done by determining our parameters here. The H naught, 74 or something, and the omega lambda and omega m, 0.7 and 0. 0.7 and 0. Whatever. So that's it. So what did we learn from this story? We learned that we started with our tuba going up and down. We found that the tuba doesn't block, the rock doesn't go back. Not only doesn't it go back, it's actually accelerating. That's our best model for acceleration. This is now plotted in time, and this is a nice thing. It's not in the things we actually observe. The other one is observing. This is not this taking the observation, putting it on the theory. The other one is taking the theory, putting it on the observation. It doesn't matter. Yeah. So basically there's current acceleration and there's past deceleration. And this is our model of the universe. It used to be in the beginning maybe an inflation stage, and then it became radiation dominated, for sure, not maybe. And then it became matter dominated, and then it became either a cosmological constant or something more exotic. Or as exotic, because a cosmological constant is really a bit exotic. So it could be a cosmological constant, could be modified gravity, could be all sorts of scalar fields. What else? There's anything else I forgot? There's probably a lot more. Yeah, but these are scalar fields, but yeah, they're messed up canonical scalar fields with kinetic terms that are very strange, and negative kinetic terms of quantum reviews, and all sorts of brains and things like that. They're also very and then, but the good news is that there's Euclid up to redshift 3, but really high precision, not like this stuff. Like I said, in 2 days it will do the HST in 30 years. So, and we only have a few points from the HST, so you can expect much more. But it's not its main goal. Its main goal is structure formation. No, don't talk about that. There is also something called Vera Rubin Observatory, similar to Euclid of precision, but ground-based and shimmy. We do similar stuff. It has the advantage over Euclid because it's ground-based and you can tweak it and develop it and change things and so on. Euclid is an L1 Lagrangian point. You can't, it's for 6 years and it's dead and you can't change anything in it if you want. This one is of a similar quality. It's American in Chile, but it's ground-based, so they can develop it and change things and so on. And there is a much more dramatic, the JW first, now called the Grace Roman telescope, that should be out by 2027, that will measure, like James Webb, almost, like redshift 10 and so on, but max of the universe. So really dramatic stuff with the Grace Roman in a few years. So there will be a lot of development, but again, these things are not mainly for supernova. But I'm just saying that the level, the search for these things is developing very heavily from the observational point of view, also from the computational, of course, and theoretical. So it's all together. I'm just saying this is a very fast-moving field. And supernova are really a slightly outdated part of it. It's really. I don't think you can do too far with it because you need other things, different, observable. As we'll try to see next week, we'll try to get these same things, omega m, omega lambda, h naught, and omega r, and all these things from different methods to see completely different, to see if they match or they don't, and if they don't, what's the problem with this model, if there is a problem. And this is the big discussion going on nowadays in the fields of cosmology and galaxies and structural formation. Anything? Oh yeah. Okay. So next week, that's what we'll do. We'll start with this fireball from the cosmic microwave background, and we'll get to here, how we form galaxies, stars, and so on, and how we get the parameters of the universe, omega m, omega lambda, from that thing, and from that thing, from the distribution. Another nascent thing also from the galaxies themselves, not only from the structure. And we'll talk about that. And Alexei will talk, I guess, about the inflation part, the very early universe, and the horizon problem, the flatness problem, and all these things we touched upon, but I wanted to focus much more on this part than on the other things. Okay, so any questions? Yes.
I get lost a little in the end. Is this result other than acceleration about the geometry of the universe? We are near flat, not flat.
That's a good point. No, we cannot prove it's completely flat. But it's
we are near flat.
To observation level, which what's the number? You know the number for flat for the omega k? What's flatness parameter? 0.001, something like that? What?
I think according to plan, something like this.
10 to the minus 2, 10 to the minus
Yeah,
3.
very
Yeah, so people think it's fun. But yeah, not necessarily. This is a very good question, because some people I know, who are very famous people, don't think it's fun. And they think some of the problems which we may talk about next week are connected to this. Some people that are really famous with discoveries about why the microwave background should be the way it is, and big things in their belt, are saying no, it's not flat really. The evidence is not final, but it's not accepted by most people. What's accepted is the best fitting parameters is flat. But you all cannot, because you have more than one parameter, you can always tweak it. And there are errors and it's very, But they don't get it from here. This is really consistent with flat. They get it more from the cosmic microwave background. The problem why it's controversial when they're saying, as far as I remember, I don't remember the details, but as far as I remember, I think it's controversial what they're saying is because from the cosmic microwave background is consistent. But you come to here and you add up other observables I'll talk about next week, it's not consistent with that. So you shouldn't look at one thing. You should look at all of it together and combine it, all the knowledge that you have. So that's it. Okay? Yes?
That means the universe is accelerating with the same rate in all directions? The same,
Yes,
within the
yes,
same
yes,
distance?
isotopic and homogeneous. Yes, it's accelerating and accelerating. On large scale. Okay? Not on the scales of, let's say, nearby galaxies.
Over the long distance.
Yes, over the long distance. Because on nearby galaxies, some of them are coming towards us, actually.
Yes.
But on the scales where there's expansion, it's isotopic. Yes.
Why do you think that the luminosity of the stars changes periodic method?
We didn't think we were observing.
Is that due to plasma interactions inside the stars?
No, it's thermal. It's like a heat engine. You compress. I'm not an expert on that. My understanding is that you compress, it heats up. When it heats up, it expands. Then it cools. And then you compress again. Why are not all stars like that? I don't remember the reasons. But the basic thing is like you compress, it heats, you expand, it cools, and then you compress again.
Like an engine.
Yes, it's like a selection. Yes. Yeah. I don't remember why these stars are like that, but probably their masses and composition. Everything about stars is their mass and composition, chemical composition and their mass, determines how a star behaves. And age. For these guys, probably the mass and chemical, how much helium, how much metal. By the way, in astronomy, everything that is beyond the hydrogen or helium is called metal. They call wood metals. They just call it metals. Astronomy is strange. They use things since Ptolemy and Right, okay, so next week we'll be talking about the structural formation and see how we get the same parameters the same way and form galaxies and do this kind of stuff.